Hello, welcome to lecture number 44. In lecture number 33, we have seen some theorems of circle, and we have proved few of them, and some homework was given to you. Now let us prove few more theorems of circle today. Before that, let us have a couple of definitions like inscribed angle. Now, inscribed angle is something like this. If you have a circle and you have an angle whose vertex is on the circle, and suppose this is A, this is B, and this is P, then we call this angle inscribed in an arc APB. So, essentially the condition should be there should be an arc of a circle, there should be an angle, vertex of the angle should be other than the endpoints of the arc, and sides of the two sides of the angle should pass through the endpoints of arc. Then we call that angle is inscribed in a circle. That definition is given. Second definition is intercepted arc. Now, as name suggests, if there is an angle and there is an arc which is intercepted by that angle, we call that arc as intercepted arc. So in this diagram, this is intercepted arc. However, it is not necessary that you have the vertex of the angle on the circle. Still, this is called intercepted arc. So essentially, what is intercepted arc? It is the portion of the arc which is in the interior of the angle which is present there. So this is intercepted arc, and hence the next theorem is measure of inscribed angle is half of intercepted arc. So, if this is the situation, measure of inscribed angle, that means measure angle APB, is always half of that of intercepted arc. Measure of intercepted arc will be its central angle. Measure of intercepted arc will be its central angle. So, the theorem is measure angle APB is half of measure angle AOB. This is what is supposed to be proved. Let us look at it. Let center of the circle be M. Now what we are supposed to prove is if this angle is X, then this angle is 2X, double of that. APB, to prove that, measure angle APB is half of measure angle AMB. Okay. Now this is a simple theorem and you independently should be able to do it. So try your best to prove this theorem, otherwise look into the solution. Okay, the solution is first join PM and extend. Now you will observe that MP, MA and MB are radii of circle, therefore they are equal. Now suppose this angle X, if we consider it as X, MPA, then isosceles triangle property will make this also X. Other angle is also X because that triangle is isosceles. And exterior angle property will make it 2x. Okay. Now suppose this is another triangle, it is isosceles but is not congruent with this, therefore this will be another angle y, this will be also y, and therefore exterior angle will make this 2y. Now the measure angle APB is x plus y, which is supposed to be equal to half of 2x plus 2y, which is true. So this is how the theorem is being proved. Now there could be few more cases. Now here I have taken the inscribed angle in the major arc, therefore things are easy. However, in the other two cases also, the construction needs to be done is join PM and extend. Okay, so let us look at the other situation where the angle inscribed is in minor arc A, P, B, and center is over here. Okay, now what we are supposed to prove is measure angle APB is half of measure angle AMB measured like this. Okay, measure angle APB measured anticlockwise like this is half of measure angle central angle AMB. Okay, as I said, the construction is going to be join PM and extend. Now again it is isosceles triangle, these triangles are equal, so therefore suppose this is x, this is x, this part of this angle will become 2x, right? Suppose this is y, then the remaining part, this also will be y, and hence remaining part here will become 2y. Again the same result will be true. Shall we consider one more case where maybe we will need to subtract? Suppose we have a situation like this and M is sitting here. Okay, now this is P is in minor arc, but its position is such that in the angle APB, M is not there in the interior of that angle. Okay, so it is outside, and therefore we need to consider separate proof for this. Again, join PB, PM and extend. These three sides are equal, 1, 2 and 3. They are isosceles triangles. Therefore, now suppose this angle is x and this total angle is also x, then which angle is 2x? Then this angle is 2x. Okay, the other isosceles triangle is this MAP. So suppose this angle is y, this angle is also y, then this angle will become 2y. Okay, now if you look at measure angle APB, it is x minus y. X is bigger angle, y is smaller angle, which is supposed to be equal to half of, again AMB is 2x minus 2y. Right? Therefore, once again we prove the same result, and hence we have a theorem, measure of inscribed angle is half of that of intercepted arc. Now, let us look at some equalness properties of circles. So far what we have discussed is points on the circle are at equal distance from the center, congruent chords are equidistant from the center, measures of all angles inscribed in given arc are equal. Now the theorem that we have proved just now, that inscribed angle is half of that of intercepted arc. So this intercepted arc, so far we are keeping the same. Arc AB which is intercepted, if we are keeping the same, and if we vary point anywhere on this measure arc P, its measure is going to remain same. That means if I draw point P here, point P here, anywhere, suppose this is P or this is P, or if we draw it here P, every time these measures will be equal. Why? Because they are half of this angle. So far this angle is not changing, the inscribed angle measures will not change, and this is yet another equalness property of circle where measures of inscribed angles are equal. Now it is going to be interesting to see, suppose I have AB over here, and I have one angle here which is P, another angle here which is Q, and if suppose this X and this is also X, converse of inscribed angle property. If the measures of inscribed angles are equal, then will those 4 points be congruent, A, P, Q and B? Now the theorem is true. Let us look at the converse of it. Converse is, in this case we are going to do it indirectly by drawing a circle. Any 3 points will determine the circle. Suppose there exists a circle passing through A, P and B and not Q. So what we will do is we will join A Q dash. Q dash is another point where QB is getting intersected. So Q dash is on circle. Therefore what we will get is, as per earlier theorem, major angle A Q dash B is also X. Okay, understand this proof. We want to prove A, P, Q, B are on one circle. However, we cannot prove it directly, and therefore what we are trying to do is we are doing it indirect proof and saying that we draw a circle and if possible Q is not on the circle. Then the circle intersects QB at some other point, maybe at Q dash as I have shown. Then by previous theorem, A Q dash B is inscribed angle and its measure should be equal to X because equalness property, and therefore in triangle A Q Q dash you find that one angle is X and the other angle is also X. The exterior angle is X and the interior angle is also X. That means they contradict to the exterior angle theorem. They contradict to exterior angle theorem, saying that exterior angle theorem says a measure of an exterior angle must be less than or must be less than remote interior angle. So measure of exterior angle, this angle must be less than this angle or this angle. In fact, this measure will be this plus this. If a triangle exists, then there exists an exterior angle whose measure is definitely whose measure is definitely going to be greater than individual interior angles. Okay. Okay. Now, next definition is of cyclic quadrilateral. A quadrilateral is said to be cyclic if all its 4 vertices lie on a circle. If all the 4 vertices of any given quadrilateral they lie on circle, that means the quadrilateral is cyclic. So if quadrilateral is cyclic, we can have a circumcircle of that quadrilateral. Now the next theorem is, when we have a cyclic quadrilateral ABCD, measure angle A plus measure angle C is equal to measure angle B plus measure angle D. This is our next theorem. Sum of opposite angles is equal. Sum of opposite angles is 180 if quadrilateral is cyclic. Now, how do we do that? Basically, if we use inscribed angle property of, this particular theorem is also easy, you should try yourself, but if not, then try to do this. Suppose this angle is Y, this angle is X, and we have already proved that AC inscribes at B, and therefore this is going to be 2X and this is going to be 2Y, but the total central angle is 2X plus 2Y, which is 360, and therefore X plus Y, 2X plus 2Y is equal to 360, therefore X plus Y is 180. This is what is our next theorem, that if the quadrilateral is cyclic, then sum of opposite angles is equal in both the cases, and therefore each one of them adds up to 180. Now, the converse of this, suppose I have a quadrilateral whose measures X plus Y, given X plus Y is equal to 180, to show that ABCD is cyclic converse. Okay, now again we will take help of indirect method. What we will do is we will draw a circle passing through 3 points and say that fourth point does not lie on it. We call this, maybe this point as B dash and join CB dash. Then what will happen? By previously proved theorem, if this angle is x, B dash lies on the circle, therefore this angle will be y. And again it will contradict to exterior angle theorem as far as triangle CBB dash is concerned. So we have got now 3 different theorems related to cyclic quadrilateral and their converses. We have done 2 of them in this lecture, 1 in the previous. So these are the properties of circle, basic properties of circle that we must know how they are true, why they are true, and we should use them in solving problems. So that is all as far as content of lecture number 44 is concerned. Or oh, there is one more theorem. Okay, there is one more theorem in case of cyclic quadrilateral. Let us do it. The theorem is, if a quadrilateral is cyclic, then exterior angle x is remote opposite interior angle. If quadrilateral is cyclic, then exterior angle of a cyclic quadrilateral ABCD, measure angle ADE is going to be equal to measure angle ABC. Now this is the simplest theorem in cyclic quadrilaterals. You can see that this angle is going to be supplement of this x, 180 minus x, and this angle 180 minus x plus this angle x is going to be total 180. Therefore, if this is 180 minus x, then this must be x. So in the beginning you can assume it to be y. This is 180 minus x by linear pair, and both of them should add up to 180. Therefore, x is equal to y. Again, the converse of this, if any quadrilateral that you have, and you see that this angle x and this angle y, if they add up to 180, then the quadrilateral has to be cyclic. These are very important theorems as far as cyclic quadrilaterals are concerned. They are very useful in problem solving, but their proofs are very simple, that if these two are supplementary, that is what is given. That means this angle, if these two are equal, that is what is given, x is equal to y, then the quadrilateral has to be cyclic, because then this is 180 minus x, x is equal to y, so 180 minus x plus x is equal to 180, and hence it is cyclic. So these are all theorems related to cyclic quadrilateral in lecture number 44. There are 4 problems which you solve. See you in lecture 55. Thank you.